Phyllotaxis algorithm. In this presentation, we continue informing you about the results of mathematical research of botanic phenomenon known as phyllotaxis. It goes about the principle of spiral and symmetrical form organization that is widely spread in the world of plants and nature in general. Our previous film, Dynamic Symmetry, demonstrated the first part of the research, which revealed the phyllotaxis growth mechanism regularities of non-Euclid geometry, namely Minkowski geometry. It is necessary to stress that the research focused on the so-called cylindrical phyllotaxis, and it revealed the change of phyllotaxis lattice in the process of bioform. Growth results from the transformation equivalent to hyperbolic rotation. Movement characteristic of Minkowski geometry. It makes it possible to present the description of structural and numerical peculiarities of phyllotaxis by means of hyperbolic trigonometry, formulae in particular, the so-called golden functions that constitute a special class of hyperbolic functions based on golden section. Thus, golden functions, golden sine and golden cosine describe the numbers of the left and right spirals, which in the most common case are Fibonacci numbers, and golden tangent is divergent angle. Thus, at first stage of the research, we have obtained principally new phyllotaxis model, which differs from the classical one, its idea and changes the angle of further geometrical research of the phenomenon in question, as well as its evaluation concerning the issue of geometrical laws of natural form creation. Then goes the next step. We generalize the phyllotaxis model for the cone case, and thus for the disk case, as disk can be viewed as an extreme variant of cone when the angle phi between the geometrics and symmetry axis reaches 90 degrees. We shall put the question in the same way as we did in the case of cylindrical phyllotaxis, namely, how the order of asymmetry of phyllotaxis lattice is changed in the process of bioform growth. Let us consider the most simple model. It suggests that divergence angle in the structure of cone lattice is constant and equals phi in 2 power. In order of symmetry depends only on the internode distances that are measured radially. The shorter is the distance between the consecutive angles, the higher is the order of symmetry. Radial lines are the trajectories of lattice vertices motion in the process of transformation. In the process of transformation, the proportion undergoes to Q and changes but any moment of the time. It is the same for all pairs of consecutive vertices. It corresponds to the idea of similarity. The order of spiral symmetry, example, the quantity of left and right spirals, is changing in the sequence which is expressed by the correlations of Fibonacci numbers. It is necessary to stress that illustrations can be considered as projections of the cone lattice onto a cross square. It is evident that the transformation effect does not depend on the angle phi, which will be taken into account further. Let us consider a more complicated variant. We set a demand that divergence angle d in the process of transformation will be changing according to the same regularity as in the case of cylindrical phyllotaxis. That is from 0 to golden section. Logically, the correlation of radial coordinates of the neighboring vertices is to change. The dependence between Q and D is the following. But at any specific moment of the time, the value Q is similar for all pairs of consecutive vertices. The demands are fulfilled if the transformation is to be done according to the following algorithm. In the starting position, the infinite row of points are situated on the one polar radius in such a way that for a pair of successive points, the correlation of polar radius is equal to golden section. Transformation of symmetry is done by similar motion which is determined by the center O and similarity ratio phi. The motion trajectories for all lattice vertices except for the point which is the end of singular radius are golden logarithmic spirals. Every vertex has its own trajectory. All the trajectories are the same, but trajectories of any two successive vertices are shifted for the angle phi. Thus, the trajectories formulae are the following. The transformation mechanism will be illustrated on the example of the points O, 1, and 2. In particular, we see that it is impossible for the angle D to reach its boundary value, and also that it is impossible for the points to reach the boundary equal to 1. The limitations are explained by the fact that instead of independent variable, we introduce into the formula pon a restrictedly changing parameter d, which is function from n. Increasing n from 0 to infinity, we change value d, which becomes the reason for speed limit and also values of angular and radial coordinates of lattice vertices. Thus, the motion of lattice points is strictly regulated, and it is characterized by the following specific peculiarities. All the points, with exception of point O, start moving simultaneously. Angular speed of the point 1 is determined by correlation between d and t, where t time that is measured from the beginning of the motion. Speed of every point is continuously falling, and it is getting close to 0. The relative speed for any pair of points is constant. The correlation of radii of two consecutive vertices is getting close to 1. The radial distance between two consecutive vertices is constantly decreasing and is getting close to 0. The value of polar radius of any vertex is getting close to 1. Thus, we observe the process of continuous vertex addition, both of the lattice packing on the disk surface and periodical growth of the quantity of the left and right contact peristices in sequence, which correspond to the phyllotaxis natural properties. And still both models have one significant discrepancy of the phyllotaxis natural properties: the lag scale. The very mathematical idea of logarithmic spiral, which the models are based on, does not suggest in the principle. In other words, these models lack limitation of the minimal size of elementary particle of the phyllotaxis structure. This size, according to mathematical properties of logarithmic spiral, goes down to 0, which is physically impossible. The answer can be found in the mathematical model of cylindrical phyllotaxis. In fact, the regularities of changes and radius p are determined by the correlation of radius r of the high cylinder of so-called elementary belt of phyllotaxis surface. That is, it means that the trajectory of the typical vertex motion on the disk surface will not be the logarithmic spiral but slightly different curve. It has the scale and mirror symmetry axis which coincides with a singular radius. Let us call it golden consine spiral. Let us compare Figure 1 and Figure 2. Figure 1. Figure 1 illustrates the connection between the graph of exponential function with logarithmic spiral to the coordinate x in the system of coordinates. X, O, Y corresponds to coordinate alpha in polar system. Figure 2 illustrates the connection between the curve and the golden consine and spiral of golden consine, which actually is GC curve in polar coordinates. Evident is the correspondence of value 2 equal to alpha. The golden consine spiral has scale which is set by the smallest value of function. Actually, the figures illustrate the analogy and difference of two geometrical ideas, which previously considered and just suggested phyllotaxis models are based on. Thus, we emphasize the characteristic peculiarities of the last variant. First, transformation of symmetry is not the similar motion. The trajectories of vertices motion are the golden cosine spirals, which, as the distance form, the center becomes similar to the logarithmic spirals. Secondly, contact peristices left and right are not logarithmic spirals, but resemble them in appearance and resemble them as they distance from the center. And 3. Phyllotaxis lattice has the scale set by the size of central circle, which vertices do not enter. The order of symmetry in the process of transformation that is characterized by the correlation of quantity of left and right contact peristices is changed according to the same regularity as in the previous models. Thus, it goes about Fibonacci numbers or Lucas numbers or numbers of any other recurrent sequences. This model, due to the scale, is fully adequate to the natural phyllotaxis. Formal geometrical difference in nature is achieved by the expense of change in cone-angle phi and also owing to the change of radial internode distance d. It means that in the natural geometry, y and d are free and mutually independent parameters. Summing up, it is necessary to note that in the topic of phyllotaxis to be studied are the issues concerning geometry of constant dynamic symmetry, the process where all pairs of consecutive vertices differ as to the indicator d, and also to be explained is the difference between phyllotaxis geometry of dense inflorescences and
infractescences
and phyllotaxis geometry of leaves arrangement. These issues will be studied in our next video material.